Greetings. Welcome to Electronic Circuits 1. I am Razavi, and this is lecture number 31. Today we will continue to look at the device physics and operation of MOS transistors and try to derive equations that represent the behavior of these devices so that we can use them in the analysis and design of circuits. But before we go there, let's take a look at what we learned last time in lecture number 30. Here's what we discovered. We went inside the transistor. We saw that there was a channel of electrons when the gate voltage was sufficiently positive, past the threshold. And then we looked at the velocity of carriers, the electric field. We ended up with a differential equation in terms of the current through the device and the local potential inside the channel. And after we solved that differential equation, we ended up with this simple relation between ID and VGS and VDS. So here's the structure that we have. And in one test, we keep a VGS constant and we allow VDS to vary. And we are interested in this drain current. So this is what we see. The drain current follows a parabolic relationship, as we can see here. There's a parabola in terms of VDS. It starts at 0 when VDS is 0, and it reaches a maximum at a certain amount of VDS, which is equal to VGS minus VTH. Now, remember that we called VGS minus VTH the overdrive voltage because it's an indication of how much VGS you need beyond one threshold to have a certain amount of channel density. Okay, all right, so this is the current behavior up to this point. And in this case, we have kept a VGS constant. Today, we want to study this more carefully, looking at some special cases and then also trying to see what happens after this point. If we follow this parabola, then after this point, the current should go down. And that doesn't sound very good. We don't want the current to go down. That's not a good device, at least not for what we are concerned with. So we'll have to see what happens there. And then eventually, we would like to have a relatively simple model for the transistor that we can use. This is an indication of a model, but maybe even something simpler than this. So we'll have to see how that goes. OK, so today, we will look at the characteristics again and consider some special cases, and then introduce the concept of regions of operation for the MOS device, and then derive a simple model. All right, so let's draw those characteristics again. So we saw that the IV characteristics that we derived last time looked like this. So we have ID as a function of VDS with a constant VGS. And of course, VGS is greater than one threshold to make sure that the device is turned on, meaning that it has a channel underneath the oxide. So we saw that we go up and reach a maximum right here. I should be careful in this drawing here. So we reach a maximum. And that maximum occurs when VDS is equal to VGS minus VTH. And we even found the maximum value here, right? So this value, the maximum current that the device would have from drain to source, is equal to 1/2 of mu n Cox W over L VGS minus VTH squared. Okay. Now, we mentioned last time briefly that the equation that is that of the parabola, meaning for the entire characteristic from here to here, can be simplified in one special case. So let me go back to that equation and show you how we can simplify it. So in this equation, what we can do is if VDS is small enough then this second order term will be negligible compared to this first order term. So if VDS is small enough, and we know what that means that this second term is much less than the first term. Then we can neglect the second term. So if the second term is much less than the first term, it means if you cross out one VDS, it means that VDS is much less than 2 times VGS minus VTH. All right? So let's consider a special case. If VDS is much less than 2 times VGS minus VTH, then the second term is negligible. And what we end up with is ID is equal to mu n C ox W over L. Then we have VGS minus VTH. And then we have VDS. So that's an approximation. All right, I just neglected 1/2 of VDS squared in that equation. Okay, so this has some interesting interpretations. First of all, we see that ID now is linearly dependent upon VGS or VDS. So again, if you want to keep VGS constant and vary VDS, we have a linear relationship. If you want to keep VDS constant and then vary VGS, we also have a linear relationship. Of course, so long as this condition holds. Okay, so for example, let's assume VGS is constant. So we have a battery connected between the gate and the drain, and we are just varying VDS. So if VDS is very small, it means that we are around here, right? This is small VDS. So around here, I can approximate this parabola by a straight line, as you can see from this equation, right? And this equation is that of a resistor, because I have the current through the device, and I have the voltage across the device. So here's the test. Here's the setup. We have a device like this, and we have a constant VGS. So there's a battery connected between the gate and the source. And this whole thing is in a box, and it has only 2 terminals coming out. So here's the device in a box, and we have only 2 terminals out here. And what we observe is that when we apply a voltage, a variable voltage, to these 2 terminals, and we measure this current, this voltage and this current have a linear relationship between them. So from Ohm's law, that means that there's a resistor connected between these 2 points. Okay, a linear resistor. How do we find the value of the resistor? Well, if you plot ID as a function of VDS, then the slope has to be inverted to find the resistance, right? You know that we have I is equal to V over R. So the inverse of the slope of V gives us the value of the resistance. So we find this slope and invert it. This slope is how much? This slope is this much, right? This is the slope. So we can associate a resistance to this structure. We will call it R. If you want to call it R on, meaning the device is turned on, right? That makes sense. And the value would be the inverse of this. So it's equal to 1 over mu n C ox W over L VGS minus VTH. So that's very interesting. It says that a MOS device can operate as a resistor, right? These 2 terminals are 2 terminals, like any other 2-terminal device you know, and we see a resistor between these 2, provided that the voltage that we apply here is not too large. Because if it's too large, then we enter this nonlinear region, right? We just want to stay around here. So is that a big deal? Is it a big deal that I can build a resistor out of a MOSFET? Well, maybe, maybe not. But there's something interesting about this. The value of this resistance actually is under my control by this VGS, by this battery. So if I pick this battery to have a high voltage, then this resistance is small, and vice versa. So this is an electronically adjustable, electronically tunable resistance, and that's why it's so useful. If it were just a resistor by itself, maybe, maybe not, but because we can adjust its value electronically by changing this gate source voltage, then it is actually very interesting. All right, so a MOSFET can operate, so we say a MOSFET can act as a voltage dependent resistor, right? Because the value of the resistor depends on VGS minus VTH. Of course, if VDS is much less than 2 times VGS minus VTH, right? That's the condition that we need for that approximation. Okay, so that's a very useful point. Okay, now the next level of understanding that we develop by looking at this equation is that this resistor can go to infinity if VGS is equal to VTH. Obviously, because if the gate source voltage is small, right around one threshold or less, then the device turns off. There's no channel between source and drain. You don't have any resistance. It's just open circuit. So that's also a big deal. Why? Because that tells me that if I draw this MOSFET in this form, so we're going to say MOS device as a switch. If I draw the MOSFET this way, what I can see is this. If the gate voltage is high enough, then I have some resistance, finite resistance between here and here, let's say 100 ohms. But if the gate voltage is low enough, the device turns off, I have infinite resistance between here and here. So that's like a switch, like an electrical switch that you're familiar with. It's not an ideal switch because when it's turned on, its resistance is not 0. But it's okay, it's not that bad. So we say that this can operate as a switch with some internal resistance when it's on, and operate as a switch that's off when the device is off. So here VGS is greater than VTH. Here VGS is less than or equal to VTH. So that's also a powerful application of a MOS device. It can serve as a switch. Where do I need a switch that can be controlled electronically? It's not a mechanical switch, not like the light switch that you have in your room. It's an electronic switch. And I can turn it on and off by applying a high voltage here or low voltage here, right? Maybe 0 volt and 2 volts. Then I can turn it on and off. So can you think of any application that could benefit from such a switch? Okay, well, remember we talked about the Bluetooth system a long time ago? So let me put the Bluetooth system up here and show you exactly what we have. So remember that in the Bluetooth system, we had a transmitter where we applied our data to an oscillator, came out of a PA, went to an antenna, the signal propagates, reaches the receiver, goes to the antenna, goes to the LNA, etc. Okay, so that's how Bluetooth works. So for example, we have a laptop on this side, a printer on this side, and the laptop is transmitting the data to the printer. Okay, but does the printer also need to talk to the laptop? Sometimes they have to do some handshaking, they have to trade some data. In other words, a Bluetooth system consists of one transmitter and one receiver, all in one package. So here, this is the laptop. It has a transmitter, but it also needs a receiver. Similarly, the printer has a receiver, but also needs a transmitter, because these need to talk back and forth. Okay, so here's the situation. Every Bluetooth system has a transmitter in it and a receiver in it, right? All right, so here's a Bluetooth system. So we have the transmitter is usually denoted by TX, and the receiver is denoted by RX. So the data comes out of, the signal comes out of the TX and goes to the antenna and goes away. And then when we are receiving a signal from someone else, it comes through the antenna and comes and goes to the receiver. Now, in general, we have only one antenna for a Bluetooth device, one single antenna. So here's a single antenna. But we have two guys that want to use the antenna. Not at the same time, but they still want to use the same antenna. So how do I share this antenna between the transmitter and the receiver? We actually time share it between them. Well, we just need two switches, right? So we have a switch from here to here and another switch from here to here. So if you want to transmit, we turn on the top switch. If you want to receive, we turn on the bottom switch. And that's exactly what happens inside a Bluetooth device, a Wi-Fi device, and many other devices. And these switches are in fact realized as MOSFETs. These MOSFETs can be turned on and off. We have one of them here, one of them here. When we turn on one MOSFET, the signal goes this way, it goes that way, and that's how we communicate. Okay, so a MOSFET as a switch is actually a very useful device. All right, so from these very simple equations that we have developed so far, we see that a MOSFET can operate as a voltage-dependent resistor, so that has its own applications. It can operate as a switch, that has its own applications, and also some interesting things. Okay, now let's go on and address the important question that we faced last time. What happens beyond this point? If in this test I keep increasing VDS of the device, what happens? So if this equation is valid, the equation I just showed you, the parabolic equation, then it predicts that the current has to fall. And that's somewhat troublesome. So that's what we would like to answer. Now, when people measured this device for the first time, they had expected that it would go down because that was the parabolic equation said. But then, when they tested the device, strangely enough, that didn't happen. So they increased VDS and measured the current. The current went up, went up, went up, and then it just stayed constant. Once VDS exceeded this magical number, VGS minus VTH. That was quite surprising. What the heck is going on? How come our parabolic equation is not valid beyond this point? Okay, so we need to study that, and let's go ahead and do that. So in cases like this, where our equation is failing, we have to go back inside the device, look at the physics of the device, and see what might be happening. So I'm going to draw the device again, the cross-section, and see what's going on. All right, so ID for VDS greater than VGS minus VTH. Right? This is what we want to study. What happens as the drain source voltage exceeds the overdrive voltage? Okay, well, we'll draw the device again very quickly. We have our source and drain here. And the source is grounded as usual. The gate goes to a battery. So that's VGS. The drain goes to a battery. That's VDS. Okay? And we are playing with these voltages. All right, so let's assume some values for VGS and VDS such that we are still over here. So last time we saw that because the drain voltage is not equal to the source voltage, the charge density in the channel is variable. So when we plotted it just very roughly, we said that the charge in the channel, meaning the number of electrons in one little sliver here, as a function of x, it starts from maximum because we have the largest voltage difference between this plate and this plate over here. But as we travel this way, the voltage difference decreases because eventually this point is at VDS, not at 0. So we see that this keeps coming down. Okay, up to here, this is the length of the device. Okay, so conceptually, I will try to draw a charge profile in here, and this is how I do it. Okay, so I hope you see this conceptually. I'll change the colors to avoid confusion with the oxide. So here, this means charge density, right? So charge density is maximum near the source and keeps falling as we go towards the drain. Okay, good. Now, the question is, can this charge density fall to 0? At some point, maybe near L. Well, the charge density can drop to 0 if the voltage difference between this plate and this plate at this point is not enough to create electrons, to absorb electrons to the interface, to this interface here. And we know what that condition would be. The condition is that this voltage minus this voltage should be at least VTH, one threshold. If it's less than VTH, then we cannot have electrons here. But that was the definition of a threshold voltage. So if this voltage, which is the drain voltage, happens to be such that the difference between these two is less than or equal to VTH, then if it's less is equal to VTH, then the charge density here drops to 0, right here. So let's formulate that condition. So if right here, this voltage, which is VGS, minus this voltage, which is VDS, happens to be one threshold, then we are right on the edge, meaning that we have maybe one electron, two electrons, but not many, right? Approximately speaking. So at that point, if this condition holds, then this charge density drops to 0 here. Okay? All right, so that's what it is. Now we write this actually in a different form. We say VGS minus VTH equals VDS. Okay, so let's make sure that we have everything under control. If VDS is small enough, if VDS is less than VGS minus VTH, then the channel charge density cannot drop to 0 here. Right? We still have some finite charge here because the difference between these two is more than one threshold. And that's where we are, over here. However, if VDS goes up and reaches VGS minus VTH, the magical number right here, then the density of electrons at this point drops to 0. Okay, so far so good. Now, let's go one step further. If VDS increases beyond this, then what happens? All right, so here I need your full attention because it's a little tricky. So we are over here. What happens? Okay, well, if VDS at this point, at the drain end, is a little more than this, then obviously there's no channel there. We know that. But where does the channel density drop to 0? Well, it cannot drop to 0 here because this voltage is already too small. So we have to go back a little bit to the point where the voltage difference between this plate and this plate is exactly this much, because that's right at the edge, right where we have a channel or we don't have a channel. So if VDS goes beyond VGS minus VTH, the point at which the charge density goes to 0 is no longer here, it's a little farther back. The point at which the charge density goes to 0 is called pinch off. So we say this is called pinch off, meaning that the channel is pinched and it has no more charge in it. The charge density is 0. So if I want to draw this quickly for the case of VDS greater than VGS minus VTH, so we're over here, then it will look like this. The channel charge density goes like this, and then somewhere around here is equal to 0. So that's my channel charge, right? This is for the case where VDS has exceeded VGS minus VTH. In other words, over here, the voltage difference between the gate and this point on the drain is already less than 1 threshold. So we have to go back and see at what point the voltage difference is exactly 1 threshold, and that would be somewhere around here. Okay, so far so good. We still haven't answered this question, but we're getting there. Okay, now, so the pinch-off point is now here. Okay, well, to see now what happens, we have to go back and rederive the equation that we derived last time. In particular, the integration limits. That's where it's important. So we have to do that. But I want also to make one remark. It turns out that as this voltage, as the drain voltage goes up, this battery increases. This point moves to the left very slowly. It's a very weak function. So the first order, we can say that as the drain voltage goes up and this point creeps back this way, it creeps back by a small amount, but the total length of the channel doesn't change much. The total length of the channel is from where to where? From here to where the channel ends, right here. Okay, so it was here, now it's a little farther back. But if you look at the entire channel length and compare it with that little protrusion, it's very small. Okay, so we say past this point, the pinch-off point is moving to the left, but by a very small amount compared to the entire channel length. All right, so keep that in mind. Now we have to go and rederive the equation from last time. I have to add a page, so let me do that. And I hope you remember all of this. We'll go to the next page and start deriving. Okay, so we say rederive the IV equation. So remember what the equation looked like. We had something like this. We said ID, integral of ID dx is equal to mu n C ox W over L integral of, then here we had VGS minus VTH minus V of x, which is the local voltage, times dV. That's the equation that we wrote last time, right? This equation is still valid. It's based on velocity of charge and mobility and electric field and all that. But there's one little change that has to happen here. Okay, so where are the limits for x? Well, this is all in relation to the charge carriers. So long as we have charge carriers, this equation is valid. So x has to go from 0 to L. And this L is really which L? This L is really, this L is really up to here. Beyond this point, we don't have charge. We cannot write those equations. So the equation has to be written from here to here. But as I said, because this incursion is very small, we approximate it by 0 to L. Okay, there's an approximation there. All right, so far so good. But here comes the big change. So 0 to L. How about this side? At 0, we have 0. The source is connected to 0 volts, so that's fine. But how about here? What voltage do I use here? In the previous derivation, we put VD, the drain voltage, or VDS, the drain source voltage, up here, because that's the voltage that we have at the end of the channel. Right? And the channel ended into the drain because we had not seen pinch off yet, and therefore the end of the channel had a voltage of VDS. But now the situation is different. How much voltage do we have at the end of the channel? Well, remember, the channel ends, the channel gets pinched off where the voltage on the channel has reached VGS minus VTH. Right? If the voltage has reached VGS minus VTH, then if this voltage, the local voltage, is VGS minus VTH, and this voltage VGS, the difference between them is VTH, therefore the channel has ended, the channel has pinched off, right? So we have to integrate from, for the voltage, we have to integrate from 0 to VGS minus VTH, not to VD, because the channel ends where the voltage is equal to VGS minus VTH. The voltage at the end of the channel is equal to VGS minus VTH. So that's the big difference that now we have in our equation. And we write here VGS minus VTH. Okay, so before we solve this, can we see something interesting here? We have a ID, all of that, VGS, VTH, V of X, VGS minus VTH, but no VDS. So ID appears to be independent of VDS, even before we find the result, right? Okay, so let's go ahead and find the result. We just integrate as we did before. We place these limits of integral in the equations, and this is what we get. We have ID is equal to 1/2 of mu n C ox W over L times VGS minus VTH squared. So this is for the case of VDS is greater than or equal to VGS minus VTH. Because this is where pinch-off begins, right? So before pinch-off, the previous equations were correct. At pinch-off and above, this equation is correct. So we have different equations for different parts of the operation. Now, what's interesting is that this says the drain current is only dependent on VGS minus VTH and not on VDS. So let's go back for a moment and see what happened here. Okay, so remember this equation, this plot. We had ID as a function of VDS. We started at 0. As VDS increased, we reached a maximum. The maximum was given by 1/2 of mu n C ox W over L VGS minus VTH squared. And then our recent derivation shows that once VDS exceeds this level and we have pinch off, we have a constant drain current, and the constant drain current, as you saw, was equal to 1/2 of mu n C ox W over L VGS minus VTH squared. Same thing as this. So it just has to stay constant. Right? Fortunately, there's no discontinuity right here. The value we predicted over here matches the value at this peak. So from here on, it stays constant. All right? So let me go back and summarize all of these on the new page to make sure that we have everything under control. Okay, so this is the equation for beyond pinch-off. But this is the equation, the old equation, mu n C ox W over L VGS minus VTH VDS minus 1/2 of VDS squared This is for the case of VDS less than or equal to VGS minus VTH. And these two are the same value when we have equal sign here. All right, so here's what we have. If we plot ID as a function of VDS for a given VGS, however much you want to choose, okay, for a given VGS, this is what we get. When VDS is small, so just mark this magical number here, VGS minus VTH. When VDS is smaller than this, we have a parabolic behavior as a function of VDS. So we go up parabolically, reach a maximum. Once we reach here, once VDS has gone up enough to create only one threshold difference with respect to the gate, we don't have channel anymore beyond that point. So we have pinch off. So we have channel starting from the source all the way to somewhere near the drain, but then we don't have any channel. So now if VDS keeps increasing, and if we assume that pinch off point is about constant, then the drain current is constant, it's given by this value. So we have two distinct regions of operation. One here, given by this equation, one here, given by that equation. We call this region of operation the triode region. Some books call it linear region. And then this region of operation is called saturation region, because the current has saturated, right? The current has reached a constant value. This is called saturation region. So for each region of operation, we have a different type of equation, and we have to be careful with that. In fact, one of the greatest challenges that circuit designers face, especially when they take classes and take exams, is to determine which region of operation a MOSFET is in. Because if we don't know which region of operation we are in, we don't know which equation to use, right? These equations don't tell us where we are. We have to know where we are before we start using one of these equations. And that is entirely dependent on this. So we have to look at the circuit, look at the device, and try to see if we are here or if we are here. And then use the corresponding equation. Okay, so these are the two regions of operations of the MOS device. Of course, there's a third region of operation, and that's when the MOS device is off. If the gate voltage is low enough, if the gate source voltage is less than one threshold, the device is off. We don't have anything, no current, nothing. It's an open circuit as we saw before. All right, let me check here and see what we can do. Okay. All right, now as I said, in a given circuit, we have to see which one of these conditions holds for a MOS device to determine which region of operation we're in, and then how we use that device, how we analyze that device. So I have a conceptual illustration for these conditions that helps me understand. It's just a simple way of visualizing things, and I'll describe that to you. If you like it, you can use it. If you don't like it, don't use it, but I have found that useful. All right, so here in the triode region, I can visualize the MOSFET as shown as follows. Let me change the color of my pen. So around here, I visualize the MOSFET like so. So remember, we like to place more positive voltages higher on the page and more negative voltages lower on the page. So I know that here, VDS, let me write it here, VDS is less than VGS minus VTH, right? So it says that if I measure this voltage difference and I measure this voltage difference, they have a difference of VTH or more if we measure it from here to here. So this difference is greater than, this difference is greater than VTH. Okay, so the way I visualize it is, when I look at the MOS device, I just look at the gate and the drain. I don't even look at the source. I say if the gate is above the drain by more than one threshold, if the gate is above the drain by more than one threshold, then we are in triode region. Okay, you don't even need to know the source voltage, provided that, of course, we know this is the source, this is the drain, this is the gate. What's the definition of source? Source is the one that has a lower potential. Drain is the one that has a higher potential. So somehow we know which one is source, which one is drain. And once we know that, then we just look at the gate and the drain, and we look for this condition. All right, now, when we get to this edge between triode and saturation, so right on this edge, the pictorial illustration that I have for myself is like this. The difference between these two is exactly one threshold. The gate is above the drain by one threshold. And now you can see what happens if we go to saturation. In saturation region, the difference is less. So I can even lower this, the height of these two, and I say this difference is now less than one threshold. So we are in saturation. If you are familiar with bipolar devices, you realize that saturation in bipolar devices and saturation in MOS devices are very different. So please do not confuse these two. Okay. All right, so that's the way to think about different voltages and different regions of operation for a MOS transistor. All right, so let's make an interesting observation. So here's an observation. We realize that if VDS of the MOS device is large enough, meaning more than one overdrive, then the current is constant. Does this remind us of something from basic circuit theory? So let's draw the circuit more carefully and see what we have. All right, so I have a battery connected between gate and source. Okay. So a certain amount of VGS that I need to keep the device on and everything. And I put this in a black box so that only two terminals are sticking out. Again, we are not worried about the bulk or the body or the substrate for now. So you have two wires sticking out. And I apply a variable voltage here, VDS, and I measure this current. And I see that if VDS varies from here to here, the current doesn't vary. What do we call that? That is called a current source, an ideal current source, right? So we see that this whole thing operates as a two-terminal device and operates as a constant current source. And we know how much that current is. We go to our equation and we say this maximum was given by 1/2 of mu n C ox W over L VGS minus VTH squared. So that is the amount of current that this guy provides. So if you decide to buy a current source to use in some sort of circuit, that's how you actually build it, right? You can't just go buy a current source from your electronics store around the corner. Now, I hope this diagram is not confusing with respect to a similar diagram that we had on the previous page. So here, I also drew a diagram like this, right? The difference is, in this case, VDS was small. We were over here. In the new case, VDS is large, so that we have passed the overdrive voltage. We have passed overdrive voltage, and we have reached a constant current. So if VDS is small, we have a resistor on our hands. If VDS is large, we have a current source on our hands. So these are two very different structures, very different characteristics. Okay, so we have a constant current source, and that can be used. In fact, in circuit design, we often need constant current sources, and that's something you will see as you progress through many different lectures and courses. Very well. Let's see what else we can talk about here. All right, so we have primarily drawn ID as a function of VDS. One might ask, can we draw ID as a function of VGS? In fact, last time I attempted it, and I sort of stopped in the middle of it because from what we knew back then, we could not construct an accurate ID VGS characteristic. But now we can. So let's go and look at that. ID VGS characteristic. Okay, so here's ID, here's VGS. We know that if VGS is smaller than one threshold, the device is off. So no question about it. We have no current up to VTH. Once VGS exceeds the threshold, we use this equation, the saturation equation, and we see that now we have a square law behavior, a quadratic behavior. So we have a quadratic behavior. So what we have here is 1/2 of mu n C ox W over L VGS minus VTH squared. Okay. Now, if VGS becomes larger and larger, at some point, we don't have this characteristic anymore. But at the beginning, we always have this characteristic. So let me pose an exercise to you. You need to think about this very carefully, and it's a very useful exercise. So prove that the MOS device always turns on in saturation if VDS is greater than 0. For any VDS greater than 0, if we build this type of structure where VGS is variable but VDS is constant, regardless of the value of VDS, whether it's 5 millivolts or 5 volts, when VGS reaches one threshold and begins to exceed around here, we are always in saturation. So you should be able to prove that to yourself, and then you can see why I wrote the saturation equation. Now beyond that, all sorts of things happen, but don't worry about it for now. That's the characteristic that we want to keep in mind. So this characteristic is distinctly different from that of a diode, for example, where the current through the diode and the voltage across the diode had an exponential relationship. If you're familiar with bipolar devices also, there we had exponential characteristic between the collector current and the base emitter voltage. Whereas here we have a square law device or quadratic device. These are the terminology that we use for these types of characteristics. Okay. So from this now we arrive at a simple model for the device, right? So simple model. Again, remember that we can look at the device in terms of its physics. We can draw the cross-section, source and drain junctions, and oxide and everything else. Or we can draw a simple symbol for the device like this. But eventually, when we are analyzing our circuit, we would like to have some sort of circuit model for the device. For a resistor, we know how to do it. For a diode, we know how to do it, right? We have a constant voltage model, etc. So here, we also would like to have a model. Okay, so the model is this. By the way, simple model in saturation. Most of the circuits that we study in this course operate MOS devices in saturation, so that's the only model that we will develop here. All right, here's a gate source. Here's the gate. Here's the source. And here's the drain. And again, we don't worry about the substrate in this course. So the device has 3 terminals, and I need to figure out what goes from where to represent what we have seen so far if we are in saturation. Okay, well, didn't we just say that in saturation the device acts as a current source? And the current source is equivalently connected between source and drain. It represents source and drain behavior. So I'll just put a current source between source and drain. And I know the value of that current source here. What's the value here? That's this value. So I will write this as 1/2 of mu n C aux W over L VGS minus VTH squared. And VGS is where? VGS is here, between the gate and the source. This is our model. Very simple, just in terms of a voltage-dependent current source. So this is very interesting because from all of that analysis, for saturation region, we arrived at something nice and simple and easy to handle. And this also helps us with our search for a voltage-dependent current source. Do you remember last time we tried to build an amplifier using a voltage-dependent current source, and we saw that we could do that. And here's a voltage-dependent current source. This current source is a function of this voltage. Now, of course, the dependence is nonlinear. We'll have to see the consequences of that, but it is a voltage-dependent current source. So maybe using this device, we can build an amplifier, and we will do that a little later. Okay, so we have a simple model that we can use. Let's just look at an example to further familiarize ourselves with this. So I just picked some numbers to get a feel for what's going on. We typically describe mu n C aux as one number. So let's say mu n C aux is 100 microamps per volt squared. A very strange unit, but that's how it is. So you bought a MOSFET, and this quantity is a property of the MOSFET. Mobility inside the oxide capacitance, these are not under our circuit designer control, right? These are under, comes with the device. Then also the threshold comes with the device. We don't have control over it. So let's assume the threshold is 0.5 volts. And I have control over W and L. So let's just pick some numbers for now. So I will pick W over L to be 5 microns over 0.5 microns as an example. You can see that in most of our equations, we usually end up with W over L. We rarely have to deal with W itself, or L itself is W over L. So we write it as this. Okay, now the objective of this example is to design a 1 milliamp current source. Okay, 1 milliamp current source. Well, we almost have everything actually. We just need one more number. So here's the situation. If I go back here, I have a device. I know it's mu n C aux on W over L. So I know this, I know this, I know the threshold, and I know the drain current. How much, what do I need to find? It's just VGS, right? So I need to find out the battery voltage that is connected between the gate and the source. So let's go ahead and do that. We say, we plug in all these numbers. So we have 1 milliamp. The drain current is equal to 1/2 of mu n C aux. 100 microamps per volt squared. Of course, we have to be very careful with our units. This is a milliamp, this is microamps per volt squared. Then we have W over L. So 5 over 0.5 is 10. And then we have VGS, which we don't know, minus the threshold, which is 0.5 volts squared. So now we can find VGS. And VGS comes out to be 1.9 volts. So VGS is equal to 1.9 volts. So we have a 1 milliamp current source. We just pick this battery to 1.9 volts, pick this device to have a W over L of 5 microns over 0.5 microns. With this type of mu and C arcs and this type of threshold, we get 1 milliamp. Is that 1 milliamp guaranteed? Well, only if the device is in saturation. Only in the saturation region do we have a current source. How do we know if we are in saturation or not? We have to look at VDS, we have to look at VGS, or we just look at the gate with respect to drain. We have to be somewhere around here, right? We cannot be over here. So if I draw that circuit again, here's what we have. We have a 1.9 volts from gate to source, and then we have some voltage between these two because that's our current source. So can the voltage across this current source go to 0? In basic circuit theory, we said the current source holds its current constant regardless of the voltage across it. You can have 0 on it, you can have negative, positive, it always holds its current. But this is of course not an ideal current source. It has to have a certain VDS before it becomes a current source. And the VDS has to be greater than this amount. So the only way this can be a 1 milliamp current source is when this voltage exceeds this much. How much is that? 1.9 volts minus 0.5 volts. So VDS here has to be greater than 1.4 volts for this two-terminal device to act as a current source. If it happens, if you use this device in some sort of circuit and you think it's a good current source, but that circuit allows this VDS to drop to less than 1.4 volts, then we do not have a constant current source. We're not here anymore. We roll down this curve, but the current varies, and that's not very good. Okay, so that is the constraint that we have on VDS in order to have a constant current source. All right, our time is up, and next time we will continue to look at some other effects in the MOS device and see how they alter these types of models that we have developed. I will see you next time.